So that one's gonna roll.
That's rolling, okay.
Okay, so then let's all get into those positions.
Yes.
Again.
Hey everyone. So several months ago, I was in a bike accident. I got doored on my way into work. My bike had a carbon fiber fork, and I was a little concerned that there might be some damage inside the fork that I couldn't see that would make it unsafe for me to ride. This got me thinking a little bit about a more broad question, and that is just how safe is carbon fiber to be used for the front forks of bikes, particularly commuter bikes like mine. Carbon fiber, or carbon fiber reinforced polymer, like I've got here, can sustain some damage. Here's another one, a tube. Say I squeeze this, you might hear it on the microphone. Can you hear that little cracking? Right? So there's actually little bits of fracture that are developing inside, and I can't see from the outside that fracture has occurred. I know there's actually a crack that runs right along here, but I can't see it from the outside. Those fractures can occur as fibers fracturing, the matrix can fracture. You can actually get fibers pulling out from the matrix, although that's a little bit less common. They can also occur as delaminations, where plies separate like that. Those things can all lead to a decrease in the load-bearing cross-sectional area, and that can decrease the load that the part can support. What I'm particularly interested in is the development of a crack, or the potential for a crack, that gets close to the critical crack length. That could lead to a sudden and complete or catastrophic fracture of the front fork of my bike, which would be devastating. So I'd like to see if my carbon fiber fork developed any internal damage during the accident that would make it unsafe to continue riding. But what I'd love to do is actually look inside without having to section this up. And so CT scanning is a great way to do that. My friend Charlie helped get us in touch with the great folks at Lumafield, and they were kind enough to offer to scan my fork. And so we're going to take a look inside this using a CT scan and look for any damage. All right, so we're here in Cambridge, Massachusetts at Lumafield, where they've got these beautiful industrial CT scanners. And so they were good enough to scan my fork, and we're gonna be taking a look at it today inside the fork, see if we can see some evidence of damage that could have originated during the accident. Hi.
Hi.
Scott.
Hi, Sarah. Nice to meet you.
I'm Charlie.
Hi, nice to meet you.
Thanks so much for having us.
Yeah, of course. Yeah, come inside.
Awesome. Could you tell us a little bit about Lumafield? It's a fairly young company, right?
We were founded about 4.5, almost 5 years ago now, really revolutionizing manufacturing and how we think about manufacturing. It's really powerful to be able to see inside your parts, but it's really hard to do that.
Yeah.
CT is a technology that's been around for decades.
So you've probably heard of medical CT scanning. In fact, I had a CT scan done of my head after the accident. It's based on X-ray radiation being able to penetrate through a lot of different material. So we can shine X-ray through an object. We can get different intensities depending on how much material has been passed through and its atomic number. Higher atomic numbers tend to attenuate X-ray radiation more. Going through more material attenuates the radiation, so you get different intensities coming to the detector depending on how much material is passed through. We can rotate the sample around like that and develop a beautiful solid model of the part and the internal features. And Lumafield has done a fantastic job on the software side of things, especially presenting that in a really beautiful way. So there's actually a lot of really interesting science behind CT scanning. A lot of it we talk about in my lectures, and I talk about it in some of my other videos. So for example, the generation of the X-rays, we take a heated cathode, heat it up, put a voltage, say usually for CT it's in the range of 100 to 150 kilovolts, and we get these electrons that come off of the cathode and they're accelerated over towards this tungsten anode. They hit the anode and a bunch of radiation is generated in the X-ray range of the spectrum. So how does that happen? Well, that's again like we've talked about before, there's a few different ways. One, those projectile electrons, as they're called, can knock an electron out, and as you know, there'll be a subsequent filling of that electron and a characteristic emission of radiation. It's what we talked about in X-ray diffraction, copper K alpha, well-defined wavelength. the majority of the radiation in the CT scanning is not from that, but it's from the projectile electron interacting with the nucleus. So you see the nucleus is positive, the electron, as you know, is negative, and so it's decelerated as it comes close to the nucleus. And that also releases some radiation. Now this radiation is it's called bremsstrahlung. It's a bit of a mouthful, and I apologize, I may have mispronounced that. That means braking radiation. It's like as if you're hitting the brakes, so it's slowing down, it's decelerating, and there's an emission of radiation that comes from that. Now that is a range of wavelengths, and that can pose a bit of a challenge for us later on. And the other thing that's interesting is that this process is pretty inefficient. Really, we only get about like less than a percent of the energy out as X-rays. And so most of it comes out as heat, and that's one reason why tungsten makes a good anode. It's got a high melting temperature, and we need to also cool this. So cooling is really important in CT scanning.
You know, legacy CT systems cost $500,000, $1 million. You need a trained person to be doing your scans. It's expensive and it's difficult. And so Lumafield's trying to change that. We're making our own hardware and our own software and really putting this in the hands of engineers everywhere.
You guys have done a really nice job making it accessible and easy to navigate around through the models and everything. So you want to show us a little bit about the machine?
Yeah, definitely. This is our Neptune scanner. We have 3 different versions of them, and they differ in the source and the detector that are in there. But they're all based on the same basic platform. We have a source on this end, and the motion stage here, so you can position your part and then eventually rotate it when we're doing the scan, and then the detector's over here, so we're capturing the 2D images that result.
I'm really excited to see the fork and see if there is any damage. But first, I guess we might be able to scan my helmet.
We scan the 2 sides of the dropout, 2 sides of the crown. This is our software Voyager. We've got a lot of tools on the top side, and then on the right hand side we've got some view settings. We can look at it in different color schemes. The colors are showing relative density, and so you can see in the legend here, the dark blue up to the lighter blues are the least dense materials, and then as you get into the reds, those are the most dense materials.
It looks like little, very localized dark blue regions, like just there, right, exactly, yeah.
So these could either be air pockets, or they could be just regions of not dense material.
So I'm really interested in looking at this region of the fork. When we first started looking at the scans, I realized as well that the carbon fiber ply orientation around the dropouts is really curious. It looks like the plies are pushed into the mold during production and in such a way that it created a fold that came out from sort of around the 12 o'clock position and extended radially from there. Any loads that are transmitted in this horizontal direction will be loading the composite in a series orientation, acting to pull the plies apart, normal to the plies, and that's the weakest orientation, as you know. Now in this scan of my fork, it looks like there's several voids that are lined up along this fold in the fabric. Near the axle itself, it looks like there's been a crack that could have originated in the accident. I'm concerned that a small amount of riding could cause fracture of the final portions of the matrix that are still holding this thing together, leading to a pretty long crack that could be close to the critical crack length.
And I think you showed me before there might be a way to measure that.
Yeah. So this is
about 1 centimeter.
Yeah, about 1 centimeter.
So definitely that would be something that would be concerning to me.
So how long a crack do we need to be worried about? That's a really great question. From fracture mechanics, we know that we can relate the stress to the crack length through this material property, the fracture toughness. What we need then is to estimate what the stress is and find a good value for fracture toughness for carbon fiber, and then we should be able to determine the crack length. The fracture strength of carbon fiber varies really substantially, but let's just take a reasonable value. We'll take 500 megapascals for the fracture strength of carbon fiber. If we're designing a commuter bike, you're facing a lot of pressure to keep the mass low, but you don't want to go overboard, make it so low that it's dangerous. At the same time, you don't want to go overboard the other way and over-design it and have it too massive. So how do you balance the amount of material, the costs, and the shipping costs and everything with safety? So engineers do that through a safety factor. So for a commuter bike, let's say we're being safe, there's probably a safety factor of around 2. So that would then lead us to say, okay, the service load is probably going to be around 250 megapascals. If we expect that in typical use, the bike would see a maximum of 250 megapascals in some portion of the fork, we could load it up to 500 before it would fracture, right? 500 is the fracture strength. So that's a safety factor of 2. The fracture toughness, let's just take a conservative, reasonable estimate here, 35 megapascal root meters. From that, we should be able to calculate the critical crack length, around 6 millimeters. We're going to be concerned with cracks that are around that 1 centimeter range. I replaced my fork with a steel fork. Truthfully, I was never really that comfortable riding a carbon fiber fork. Personally, I'd like to see every manufacturer of a carbon fiber component using a CT scan to validate that their design is reflected, their design choices are actually reflected in the part that's made. I don't know if that's the case here. I was a little concerned with the way some of the plies were oriented. It would also be great to see CT scanning used to validate that parts are safe for people to continue using after an accident. End of the day, I guess the conclusion really is, if you ride a carbon fiber front fork, please be careful. Inspect it after a bump or an accident, and ride safe. So, hey, do you think there's a problem with this fork? No, obviously, it was in an accident. A friend of mine, Matt, was in an accident, and clearly there's damage to this limb here. But the intact limb was actually really interesting to look at. There's a tiny little feature there that you probably can't see on the camera. It almost looks like a wrinkle. And I saw that and I thought, hey, if this was loaded this way during the impact, that would be the tensile surface of the beam. Maybe there's some damage there that we can see. So I reached out to Sarah at Lumafield. They were good enough to scan this limb here, the intact limb. And we can see that there's a little crack propagating between the plies from the surface, right through the plies, and then propagating along between the plies, a distance inside the fork, almost going right to the interior surface. So bear in mind, this crack, which is pretty significant, is barely visible from the surface.